All right, in this video, we're going to continue the conversation of long division, make them a little bit more complicated, but importantly, we'll introduce the factor theorem, which is incredibly important moving forward and will lead us to the fundamental theorem of algebra. So in this example right here, we're being asked to divide 2x cubed minus 5x squared minus 18x plus 45. We're going to divide that by x squared minus 9. This is a really important thing that we didn't do in our last two examples, but when we do this long division, every power of our variable, x in this case, needs to be represented in all of the polynomials we're interacting in this division. What I mean by that is here, we have this quadratic or degree 2 term, but we don't have a linear or x or degree 1 term. We just have this constant. So when I do this division, this is really important, is what I'm first going to do is write this as x squared plus 0x minus 9. What this move does is lets us keep things organized. Importantly, when we write out numbers, we use zeros to denote powers of 10 that we don't have a value. We don't have that same structure with polynomials. So what's important is no matter what degree you're a divisor or the polynomial you're dividing into, whatever degree that is that every degree term is represented in your representation. All right, so that's the only tweak I needed to do. Now I can just perform the long division. Importantly, again, when I do this, I'm only focused on these lead terms. So what times x squared is 2x cubed? Well, that would just be 2x, because 2x times x squared is 2x cubed. And now dealing with this middle term, just show you how we're going to use this to keep us organized, is 2x times 0x. I'm going to write that as 0x squareds. It's really just 0, but I want to keep this x squareds to keep my like terms all organized and in line. So I think of this as 0x squareds. And then 2x times the negative 9 is negative 18x. Then I subtract that from what I had. So let's see what my remainder from that move is. 2x cubed minus 2x cubed. Well, as always, that should cancel out if I did it right. Negative 5x squared minus 0. Well, that doesn't do anything. So this is negative 5x squared. In this case, I have negative 18x's and then minus negative or plus 18x's. So those actually cancel. But what I'm going to write here is 0x for exactly the same reason I introduced that 0x up here. Bring down this 45 and continue this process. And actually, this will be my last step here. What do I need to multiply x squared by to get negative 5x squared? Well, that's just a negative 5. Multiply that to get negative 5x squared. Negative 5 times 0x is 0x's. Negative 5 and negative 9 is a positive 45. And things are looking up in the world. Look at this. This subtracts perfectly. I have no remainders. 45 minus 45. I get a 0. So again, what I've found here is that when I take 2x cubed minus 5x squared minus 18x plus 45 and I divide it by x squared minus 9, the result is 2x minus 5. Though importantly, how I will always be playing with this is I take this 2x cubed minus 5x squared minus 18x plus 45, and that equals the x squared minus 9 times the result 2x minus 5 right there. And though it wasn't asked of me just for kicks, I do always feel like I want to try to completely factor this. I realize this is a difference of squares, so I'll rewrite this as x plus 3 times x minus 3 times 2x minus 5. And then just to go one more step, because this is what we really want to be doing with all this, I now know that I have zeros at x equals negative 3, x equals 3, and x equals 5 halves. All right, now feels like a good time to talk about the factor theorem. The factor theorem states that f of c equals 0 if and only if x minus c is a factor of f of x. Now, you probably have already had an intuitive understanding of this through your work previously in factoring quadratics and finding zeros and x-intercepts. But this is a really important statement. I also want to say this if and only if is saying that if this statement is true, then this is a factor, or if you find that x minus c is a factor, then you know that c is a 0. And in fact, that's pretty dang obvious from right here, and I wrote this here, is that, well, since x plus 3 is a factor of this polynomial right here, then negative 3 is a 0. And again, I'm saying that because x plus 3 can be thought of as x minus negative 3. It would also follow then that since x minus 3 is a 0, or is a factor, excuse me, then 3 is a 0, where c plays the role in these cases. The only one that feels a little weird here is that we have x equals 5/2 as a 0, but I don't see that as a factor. And I just want to rewrite this just to make sure this is incredibly clear right here. So if I take this 2x to the third minus 5x squared minus 18x plus 45. I do know that I have this factored form right here that I'll just rewrite real quick. Again, I can see all the zeros from this, but this is not directly written in this method. What I'm going to do, just to write it in this form that's being described here, I'm going to factor a 2 out of this factor right here. So I'm going to divide each of these terms by 2 and multiply by 2 out front. In fact, I'm going to write that 2 out here. If I divide both these terms by 2, what I get is x minus 5/2. And you don't need to write it like this, but just to clarify this factor theorem right here, when I've written it in this form right here, I can then identify the zeros by seeing what's being subtracted. Again, the only little thing I would need to do is rewrite this, or just do it in your mind, as x minus negative 3. If I do that, then I can identify immediately all of my zeros. My zeros are negative 3, 3, and 5/2. All right, here's a fun example that ties together much of the stuff we've talked about before. It's really building to what we're going to see very soon in the rational root theorem and the fundamental theorem of algebra. In this case right here, we're given this polynomial f of x equals x cubed minus 6x squared plus 32. And what we're being told is that it has a 0 at x equals 4 of multiplicity 2. This is really important. So two things. What we know about this statement, we know the factor theorem says, is that x minus 4 must be a factor of f of x. That if we divide out x minus 4, we should get a remainder of 0. That's what it means that this is a factor. But we also know that it has a multiplicity of 2. So what we know is that x minus 4 as a factor shows up twice. Therefore, what we know is that x minus 4 times x minus 4 times some unknown factor here must equal this original polynomial of x cubed minus 6x squared plus 32. So our job is to find this extra factor right here. We know that whenever we find this factor, then we can find the 0. That's what the zero factor theorem says. We know that these must be factors by the zero factor theorem. The way to find this is through division. What I'm first going to do, and you could optionally, there's two ways to attack this. I just want to say, since we have a 0 of multiplicity 2, I could take this and divide it by x minus 4 twice. Or for me, what I think is a little bit of a hack and a little bit quicker is I'm first going to multiply this out. And so this is a perfect square trinomial. This will be x squared minus 8x plus 16 when I FOIL that all out. I'm looking for this unknown factor right here, but I know that it results in this. So all I'm going to do is I'm going to use polynomial long division. I'm going to take this polynomial, I'm going to divide it by this and hopefully result in a factor that makes it very clear what my 0 is. At this point, we feel pretty good about long division. Let's just do this quickly. I do want to make the note that I had to add this linear term to this polynomial right here. It had a degree 3, degree 2, and then a constant. I need a degree 1. I've added right here just to keep things organized. But we move forward, lead terms. I need to multiply x squared times an x to make it x cubed, and then I distribute through all three of these. I get x cubed, negative 8x squared, and a plus 16x. I'm then now going to make sure I subtract all of this jazz. And the x cubes cancel. I have negative 6x squared plus 8x squared, which results in 2x squared. 0x minus 16x gives me negative 16x squared. And then bring down this 32. And then at this point, I need to multiply this x squared by a 2 to get 2x squared. So plus 2 here. Things are feeling really good here. 2 times the negative 8 is a negative 16x. 2 and the 16 is 32. Everything cancels out, giving me a remainder of 0. And that's important. I absolutely expected that because I expected when I divided by these, I wouldn't get a remainder because x equals 4 is a 0 of multiplicity 2 of this original polynomial. But what I found is that this results into x squared minus 8x plus 16 plus x, or times x plus 2 times x plus 2. Again, we've used the factor theorem to take this information, knowing that we have this as a factor twice because of the multiplicity statement. We now have this cubic completely factored, and we've identified the other 0 of multiplicity 1 at x equals negative 2. Long division of polynomials is rarely a fan favorite of students, but it's an incredibly powerful and important process. It gives us the ability to tackle higher order polynomials outside of quadratics, finding their zeros and breaking them down into their factors.